Hello, everyone, and welcome to today's BA Collab, our webinar, Filling with Finesse, matching your fill process to your beverage. My name is Joe Damgard. I'm the Sales Activation Manager here at the Brewers Association. Before we get started today, there's a few logistical things I'd like to go over. First of all attendees have automatically placed on mute to eliminate any background noise during the event. We ask that you, if you have any questions, you use the Ask a Question feature at the bottom of your screen. We'll get to as many of those questions as possible during the Q&A session after the presentation. If you have a question and you see it, if you see a question that's already been asked and you'd like to know the answer as well, be sure to vote that up using the up arrows on the question box. The most popular questions will float to the top, so we're sure to get to those during the Q&A. You can also make any comments throughout the event using the chat feature on the right-hand side of your screen. But be sure, if you do have a question, to use that Ask a Question feature at the bottom. If you have any connectivity issues during the seminar, or you notice your video is lagging, there's a few things you can try. First, do a quick refresh. That usually works with most issues in Crowdcast. If that doesn't work, try clicking pause on your video player, wait a second, and then hit play again. If neither of those options work for you, you can try lowering your video resolution by hovering the mouse over the video player and clicking the gear icon at the bottom right. From there, you can lower the resolution to either 720 or 360p. Finally, worst case scenario, you can try putting your video in compatibility mode. To do so, click the link at the bottom left underneath the live stream that says Get Audio Video Help. You'll be prompted with some information about compatibility mode and how to activate it there. Last but not least, we will be recording the event today. It will be available at this very same link shortly after we wrap up. If you'd like to download the presentation slides from today, you could do so with the green button at the bottom of the screen. That's about all that I have today, so I'm going to hand it over to our speaker, Alexis Foreman, co-founder of Wild Goose Filling. Alexis, why don't you go ahead and take it away?
Well, okay. Thanks for the introduction, and yeah, it's great to see everybody chiming in here, and glad we get a chance to dig in and talk about some cool stuff. So, without further ado, let's talk about this. We're calling this Filling with Finesse, a practical exploration of filling theory, methods, current technologies, popular mechanisms, and equipment design implications. Sorry, I got to move my monitor here. There we go. Now I can read what I wrote. Here's a quick overview. Some of the stuff that we're going to talk about. There's some introduction. So who I am. Mostly what the background is. We're going to have to talk about some science and talk about, hopefully, some fluid dynamics and stuff like that to really get the fundamentals down so we can understand why these things work. I'll go into some definitions of what this technology is. So when we're, hopefully talking about it, or when you're talking about it in the future, we can all be on the same page and using the same words. And we will talk about some of the other film, some of the fill methodologies and some of the technology that's out there and sort of what it means and how it works, and the pluses and minuses of what's there. There are things that we're not going to cover. The first one is going to be DO and O2 pickup. Everybody says, okay, I'll talk about it a little bit right now, but everybody says their filler is the best for DO pickup. This one's better than that one, everything else. And you guys, hopefully by the end of this, will see that really it's not the mechanism, it's really how you're using it. And you can get great DO or terrible DO with any fill mechanism on the market. Other things we will not talk about are politics, COVID, definitely not religion. Well, actually, there's a lot of things we're not going to talk about, obviously. So let's dig in. So who am I? I'm one of the founders of Wild Goose. We started making filling machines a long time ago. We've put a lot of them in the field, so I've been doing this for a long time. My background is in chemistry. Before we started making automation, I was doing, pharma, drug dissolution, all kinds of stuff right there. So forgive me if if I get a little too heavy on science. But we're going to have to talk about some science. So then after that, I started really designing and implementing brewery automation, designing our filler systems and what have you. And now we have a fantastic team of engineers that I'm an active part of that is continually working on making our stuff better and better understanding what we've got. So why are we here? Feel like Carl Sagan summed it up pretty well. If you want to make an apple pie from scratch, first you must invent the universe. And of course, I scratched that out for package amazing beverages. As it turns out, carbonated beverages are complicated. There's a lot going on here. It's not just water and gas. There's all kinds of organic compounds in there. The viscosities are different. We have a lot of things going on. You notice that different recipes hold foam differently. Seltzers foam different than beer. Seltzer water in general, alcoholic seltzers foam differently from regular seltzers. So there's clearly complex chemistry and complex stuff going on here. And we're going to try to understand a little bit about why this is so complicated and what really affects that we can help control and what we can work on by understanding what's here. So as if fluid mechanics isn't complicated enough, we have chemistry and actually thermodynamics in here too. But don't worry, it's not a big deal. It's just your ultimate quality and finished product that's going out to your customers that's in the mix. So a little tongue in cheek there. It is important. You want your packaged product to be the best it can be. So hopefully we can help make that better for everybody. One of the things I'll note here is you guys are going to see a lot of these. These are all computer flow simulations that we did in-house here at Goose, and there will be little points of each one, and we'll get into it a little more to talk about. Each one of them here is sort of here for an illustrative purpose to hopefully I can help demonstrate some of the concepts with pretty pictures, and they're also pretty pictures. So proper filling takes proper understanding. We're going to go through, there's a bunch of factors at the beginning of, your product conditions are a big one. Temperature, the transfer to the packaging area, the transfer to the fill head, the distances, the line regulation, the line restriction, the elevation, the product inlet integrity, the way all of those things play a factor in how well your product pours. And then there's the specific filler aspect of it, of what does your fill system look like if you're evaluating different ones. We'll go into the anatomy of each of those and go through the different technology of how they work, how they fill, how they detect, and then what does it really mean and why does it really matter. So hopefully we'll be able to shed light on this. I know it's, like I said, it's, first we have to create the universe, and hopefully we can really dig in and make this, what is a very complicated thing, appear a little simpler by the end of it. So without further ado, we're going to get into the chemistry of carbonation here a little bit. So I have two major factors here. I'm sure everybody here has seen this chart before. And this is a plot of how much CO2 you can put into, this is water. So works analogously, and all these are idealized anyway, so it's never quite this smooth, but it gives you the indication that, sorry, I gotta slow this up a little bit, that as we go for the temperature in C, the closer we get to freezing, the more gas goes into solution. And I think everybody kind of inherently knows this. Cold beverages and cold carbonation is way more stable than warm carbonation. So what it means here is as we increase in temperature, and this only goes up to 35 C, this graph, as we get down here, we're holding a third of the gas in solution. So these degrees matter a lot. 35 C, sorry, 35 C is body temperature, so 36. So our sweet spot is obviously down in here, but even from freezing to 2 to 3 degrees, you can see a huge difference in gas solubility. This one's pretty basic. Keep it cold. That makes sense. The one that is less intuitive is the solubility and pressure. So we know that when we're carbonating stuff, we have to maintain a head pressure to get the gas to dissolve in the liquid. And that's what we've got here. As we increase that pressure, we push more liquid into the gas. So, that's obvious. And where this gets less obvious is at some point it doesn't hold it anymore. If your pressure drops, you start generating bubbles and what have you. It doesn't hold it. There's a saturation point. And the other hard part about this is that the fluid dynamics here make a huge difference. So I need you guys to look at this and remember this a little bit, because we're going to talk about this later, and I don't want to go back through 5 slides. So if you look at this, we've got this is a cross section of a product tube, 1.5 inch tri-clamp, going into little hose barbs. And what we've modeled here, and this is actually the velocity, and I'll talk about this in a minute, but what you can see is we have slow velocity in the blue and really high velocity in the reds as the color gradients go. So what this translates to is, okay, remember this, and this is on the next slide. So you can see all this red here, and this is parts where the fluid's going really fast. And that's not super awesome. So let's see, we're actually going to do this. I'm skipping 2 here. So we'll talk about the pressure here a little bit. So as we go through these things, we have pressure, velocity, and vorticity are 3 words that we're going to talk about. So as we have a carbonation level, we have to maintain a pressure. So that is actually this one, right? Everybody's familiar with this. So we have an equilibrium PSI, and this is the head pressure that has to be on the tank. And then here's the temperature. And then here's our chart of what we want our carbonation level to be. So, if we want a carb of 2.7 at 30 degrees, we maintain 9 PSI or whatever we have. And this is, please don't quote me on these numbers. I made this to make it look pretty. There, I tried to be accurate with it, but obviously there's a few things here. So there are almost nothing carbonated down here. This is where we deal with gravity filling. Atmospheric fillers get into this range, and obviously you have a much wider range with a counter pressure filler, and we'll talk a lot about that later. So to go back into here, we want to look at all of these things here. So we have our desired carbonation level really dictates what the head pressure on the whole system is going to be. So we call it 15 psi for round numbers. So we have to have the vessel at 15 psi to say we want things at carved at 2.7 for our 2.6 or whatever it is for our desired recipe, right? So the biggest trick here is controlling the pressure drop through the whole process, because remember that the pressure is a big part of the gas solubility. So part of this here is the velocity through all of these tubes and into the different things and into the vessels. We up here, velocity shows how fast we're going. That the vorticity is a measure of the turbulence, and the turbulence is a measure of high and low pressure, right? So if we have, a nice stable beer, if I open this right now, it's fine. So if we create a bunch of turbidity and velocity, we change the velocity and generate a bunch of vorticity. Now the can's harder. Anyone think I should open this? Of course not. We just knocked all the CO2 out of solubility because we created a bunch of vorticity and turbulence. So that's what a lot of these pictures look like here, are to show the relationships between them. Now, obviously, they're not directly, they don't exactly one-to-one correlate, but they rhyme. So that's sort of the point that we're getting to here. So sudden transitions in pressure create breakout and loss of CO2, shake the can. So the key to the retention and non-foaming is management of the pressure through the whole process. Every single filler, no matter how much money or how little money you spend on it, how big, how fast, how small, hand filling, your draft system, every single filler has to go back to atmosphere at some point. So, these things don't come with, you're not putting it in without the seam on, you have to cap it and seam it. So at some point, this thing has to be vented to the air. That's also why I'm not going to talk about DO anymore, because at some point they all get vented to air. We always have to hit atmosphere again. So the trick in these designs and the trick in how to do this is how well do you manage that pressure drop? So how do you manage it from where your desired carbonation set point on your tank to getting the beer into the package, into the atmosphere. So hopefully that lays a few of these things out. Oh, so here we go. So I got a little ahead of myself, but this illustrates it a little better. So here's the vorticity. You can see we have, the velocity, basically as these things hit and we see the swirls here. This is sort of the patterns and the fluid dynamics of going on. We can see the velocity difference as it comes through the tube, going really fast to going really slow in here, and how the height of this matters. And we'll talk about that a little bit more. But then it also translates very much to the way the pressure gradient in the whole system affects everything. So this one and this one are sort of the rough the analogies, right? So this is the same plot. This one's pressure and this one's velocity down here. So you can sort of see that they're loosely related, or related enough to talk about it anyway. And they look pretty. Okay, so now that we are roughly in there, and I hope I didn't lose everybody, we're going to talk about a few of the different methods that the words that get tossed around and the methods that are used. So people seem to use gravity and atmospheric filling interchangeably. They are different. Gravity is a means of the liquid transferring from wherever it's being held and into the package by simply the force of gravity. This is used very commonly in distilled spirits. It's used in, you empty the water in your tap room, for example, like when you have your jug sitting off in the other room, or for your customers to come up and fill their water. That igloo jug with the ice water in it and the solo cups next to it, that's a gravity filling system. Simple. Obviously there's way more complicated ways to do it with accurate volumes and what have you, and automated and fast. But the method is using gravity to push liquid into another container, so that it's great for water, for solvents, for distilled spirits. Most of those use it. Wine uses it frequently. Paint, whatever else we've got. So atmospheric fillers, on the other hand, take liquid from a pressurized vessel and transfer it into a container that's open to the atmosphere. So I know I just said they all go to atmosphere eventually, and that's true. Atmospheric fillers don't have the vessel pressurized. So we take it from our pressurized beer tank, run down the line, and then into the container without applying anything, without sealing the container. And counter pressure on the other end of it is that same transfer process from a pressurized container, pressurized vessel into your container, but it actually seals the container and applies pressure to the top of that container so that you can better control your release of, you have more control over the pressure in that regard. And we'll get to that. So anyway, I want to make sure we're all on the same page with these things. And hopefully that makes sense. So this is a big slide. We're going to talk about, this is, forgive my rudimentary graphics here, but this is kind of a nice block diagram of the journey of your product from effectively your bright tank and into the filler. So let's walk through this here real quick. So up here we have our product tank. There we go. Up here we have the product tank, and we have our beer. Let's call it beer. So in here, depending on how big this tank is, if this thing is a 3-barrel tank and it's 5 feet tall, the effective gravity on this isn't going to be huge. You've got a 300-barrel tank and it's 60 feet tall, you're going to see a pretty big pressure difference from your first barrel to your last barrel. So that matters actually quite a bit. The next one here is maintaining your pressure for your carbonation, and then you want to make sure you're maintaining your pressure all the way through all of this. So how much head pressure can you actually apply to your tank? That's a thing. They all have PRVs. Most of them are set at 15 PSI. I personally have seen plenty of sketchy things happen with them where they get taped over because people need to be pushing at 18, or they get, whatever it is. It's just another one of the factors here. Just knowing that is your tank pressure rated is actually a legitimate question. And the CO2 head pressure is another major factor in here. Like, this is probably one of the big driving ones. As you empty this liquid portion, the empty portion at the top gets bigger, so that gas expands, you lose your pressure. So we frequently see regulators iced up because they can't feed CO2 into the tank fast enough as you're filling. Maintenance of this is really, really important. So then as we travel through here, we get, into the product line, right? So usually we have, you have 2 or 3 valves down here, a bunch of tri-clamps, a bunch of everything else. Think about that first picture where we had showing the velocity going around those corners and in those restrictions. We get points there where you can see potential breakout. If you're on the fringes of temperature and pressure, that's enough to make you get breakout right there. So as we continue through here, a lot of people will do hard process piping. They'll go up into the ceiling. They'll go down into the floor. All of these things, if you have a tank that's sitting here and then you have a 20-foot clear ceiling, gravity matters. So you're going to get pressure changes in there too. So it's just knowing what you're working with. And then obviously the other big one here is how far from the tank are you to your packaging line? And I've, gradiated this one so that we can see that every bit of this product line that is not insulated, or even if it is insulated, there's no way your room is as cold as what your product should be. You're going to pick up temperature as you go through your lines. And when you stop, then it sits there and warms up. And when you're flowing, it's better and it stays cold and what have you. So you really have to be managing that portion of it also. And the other one here is having lines that go up and then go back down. So if you've got air bubbles or whatever that are getting caught in these lines, or places where every one of these tri-clamps, if you've got a little bit of a pinhole leak, a bad gasket. I know I wasn't going to talk about DO, but that's a big part of a DO discussion also, is if you have bad tri-clamp gaskets, you get air ingress, and that is enough to really screw up your dissolved oxygen. It's also enough to screw with the pressure of your process lines, and ultimately affect the way that your beverage pours. So, depending on these distances, what have you, we see a lot of things where there's process equipment. Does it take a pump to get from here to here? Are you picking up so much heat in your lines that you need a heat exchanger? Are you pasteurizing? On and on and on. So there's all of these things will affect this. You'll either pick up temperature or have pressure fluctuation or turbulence or what have you in here. So in a lot of instances, you can push this into a buffer tank or a pressure bowl. And depending on, we'll talk more about these, but effectively, if you have a lot of this going on, this is a really good idea. So you give your product a better chance to settle out. You give it a spot to sort of relax and calm back down and let things go back in. Solubility is not instant. It takes time to carbonate something, right? It takes time to push gas into liquid. It takes time for things to dissolve. So the more time that you have, the more likely your gas is going to stay in solution. So if you give it the break and let it settle a little bit and give a nice regulated pressure spot where it's in there, you have a chance to really just even all this out, and it helps. So then as we come down in here, there's obviously, very few single head fillers out there. Obviously there are a handful, which makes this pretty simple. But then most of the time there's multiple fill heads stacked up. So there's an inlet manifold here. And what does this look like? As you guys saw in some of these other, our other flow simulations, there's a lot going on in there. It's bending corners. This one's going to be different from this one. What's the line restriction here? What's the line restriction here? How all of these things will affect how your beverage is behaving. And then of course we have the other part of this is where this is sort of a diagram of, we have an empty container in, something happens here. Most of the time there's a pre-purge with CO2 to push the air out. Counter pressure or not, most of the time we see people doing that. And then we go through and do a bunch of different fill methodologies. So I'll talk about, each one of these in more detail as we go. But, you can sort of see there's a bunch of different methods to go. There's counter pressure ones where you're pushing in and venting out. There's ones that are open to the atmosphere. And then eventually we hit atmosphere because there's no lid on this yet. So we go off to the lid pick and off to the seamer. And that's where all the DO magic happens. In here, and here is a lot of it. Obviously doing this right is most of it, but this is, I don't know. They all play in, and I said I wasn't going to talk about that. So anyway, trying to think if there's anything else we need in here before we get going too far. No, I guess not. Okay, so let's talk about this first one. A lot of basically the simplest way to do this, and there are a lot of fillers out here that have this method, and it is basically just it's almost like a draft system. You're taking a bunch of 3/16 beer tubing, running it effectively from the bottom of your tank and into your fill nozzles. There's a lot of, you lose. The nice thing is you get a nice even line restriction through this whole thing. Your pressure drop is really nice and consistent. You can sort of see here, the reason I've got this picture up is you've got a very consistent flow through here. And if this gets more restricted, that slows way down and you get, an easy, it's like your draft system. You don't have to mess with your draft system that much once you get it dialed in. The biggest thing here is adjustability. And the other one to consider is what's happening right here. So if you guys remember that slide that at the very beginning where I had the manifold and the little tiny orifices at the top of it showing this area and how that diameter was really kicking up a lot of stuff, and a lot of, increasing velocities, dropping pressures. And that is a very common spot where you're going to get a lot of breakout. So the big point here is that if your product conditions are stable, if you're in the sweet spot of you're cold, you're not overcarbed, most of the time, all of these little things don't make any difference. You can use very simple, if your product is stable, the little changes in here, they're not going to screw you up. It's when you're trying to push warmer product at higher carb levels, long distances and all of that is when all of this stuff really starts to make a difference. So we see that, you see this kind of thing happen here. And I've personally seen where this manifold, where you have an 1.5 inch line going into a bunch of 3/16 hose barbs, you get foam right here. And that there's not a lot you can do about it. Basically you just have to figure out how to get your tank colder or drop your carb level. So these systems are all pretty typically simple. There's a shutoff valve that will say when it's full, a conductivity probe is typically put in at a fill level. We see it on a few different systems. And the conductivity probes are good. They give you a level in plenty of instances. I know from the research that we've done on them, some of them can tell the difference between foam and beer according to the manufacturers. Some of them can't. It's just one of those things where it's a very simple means of, hey, there's liquid here, shut it off. Adjusting the fill height then involves moving this and then playing with a timeout to say, okay, I see liquid here, shut off X amount of time after that. And that assumes your flow rates are constant. That assumes your inlet pressure is constant and you're not having too much change over here. So you can most systems now have tweaks for that to be able to control the fill volume a little, as accurately as need be. This one shows another configuration that we've seen out there, which is a bottom actuated with a ball valve on it so that you get flow around this. And then, you only have, you basically have a larger diameter tube. So you're getting more velocity out of here. This one sort of shows how you're really kind of ripping through here if you don't have the center tube in it. So we've got, a very stark difference as that small diameter goes into into the larger vessel. This is obviously a large diameter fill tube. I don't know that a lot of people would try and actuate this from the top, but it does sort of show that as you're coming down an open straw, you have just a very set, so your velocity drop is pretty significant as you go through here. You need to be cognizant of that. With the small tubes, obviously what you sacrifice, the small tubes and the small line, is flow rate. So you can only push so much liquid so fast through one of these little lines. So that's really where it ends up. It's made up for on occasion by adding multiple tubes. So there's plenty of systems that have, 2 or 3 fill tubes to say, okay, we've got a dual stage pour, but it's really one of them starts and then the second one starts, or what have you, or just a single stage in this instance with a larger diameter, and you shoot for laminar flow around the ball. Let's see. Feel like I covered that one reasonably well. So the next one brings us to some form of line restriction on the line. So this is also showing sort of the same thing. We have a super high velocity here on an unrestricted line, and you see it red all the way through, and then it goes, I guess this is meters per second, so it's actually pretty significant. We're going from 0.5 meter a second to almost 0 as it hits, and you can imagine this pressure gradient in here is pretty significant. So in order to do that on a larger diameter line, you need to put some restriction in here. So as you have your product tank, again, that makes this interface easier, right, than the one previously, because you have a larger diameter here. You're not getting as much restriction. Your rates aren't as fast through there. You then come through, typically there's either a flow meter or timing on these systems. Your flow meter will tell you when it's done. I forgot my little dotted line. And then you go through some form of plate restriction here that is kind of a set and forget. I've seen this done a few different ways, flat plates, fancy valves, this kind of thing. So the trick here is that this is a single mechanical simple adjustment. The nice thing here is it gives you more bandwidth. You can, try and maintain optimal fill speeds. I mean, let's be honest, nobody likes to sit in front of a canning line or a bottling line, right? We want to be done as fast as we can. So we really want to make sure we're getting the most speed that we can out of our fillers. So the idea here is that, you want to fill as fast as you can, but as you guys have seen, if you've dialed in your draft system or just dumped a beer into a glass, the faster you go, the more it's agitated, and you can't just open it all the way up. So that's what the restriction part is here. So you want to be able to dial in and go as fast as you can and still have good fills. So this helps in some regard there. If you have this large diameter line without this, you're at the mercy of, your tank size. If you have a small tank, it might be okay. You're trying to go to a big tank and you have high pressure in here and a lot of gravity, there's no way it's going to come out of this so fast that you're basically trying to fill a can with a fire hose. That doesn't work. So that's what this is all about. And then the idea here is that you run through the flow meter, it counts as much as you can. You make the assumption that everything that went through here ends up in here, and you shut off your fill and get a nice fill system at that point. So the trick with this then on a lot of this is you have, it's limited adjustment. You're stuck to so it's a single stage pour, which means I'll talk about subsurface here in a minute. Single stage pour will make more sense, but the idea is you want to be, you can pour faster when your nozzle is under liquid than you can when it's in the open. So we'll talk about that again in a minute. The nice thing is there's some simplicity here and, some adjustability. So here's more of our art. So this is variable line restriction configuration. This is what is on all the goose lines. We have patents on it. So the way that this goes is we have our tank. We have a single, this in our instance is a full 1.5 inch beer line. We have an optional buffer tank. you can or cannot use flow meters because we can adjust this as it goes. So the idea here is we can let the product come through, and we have a small, a 3/8 diameter silicon tube here that comes through, and these are our pinch plates that create an individual pressure drop across each one of these nodes. So instead of trying to flat out reduce the pressure across the whole thing and decrease that velocity and the vorticity in one step or one sustained step, we do it in multiple small steps. And that's actually, again, part of the patent. So then while that's going on, we can adjust this on the fly also for multi-stage pour. So we actually have an actuator here that opens and closes this to change that line restriction and then change the fill velocity. So if we look over here, you can sort of see this is a model of a nice model of the fill sequence here. And what we have in this one, this is a little different. This red is the gas that's in the container, and the blue is the liquid. So this is stepping through, and I can't remember what the time scale is, but the end of it is a 1.5 seconds. So it's all really fast. So you can sort of see as it comes out, the faster this goes, if this is going really fast in these, you're going to get a ton of turbidity and breakout. But as the nozzle buries and it remains right below the surface, we get smoother pour. So this, this is an indication. We modeled this in a few different ways to where we have, this is modeling it being just off the bottom of the can, and you see there's a lot going on here and a lot of big changes in the this is a vorticity plot versus it being in the middle versus being right at subsurface. And I'll spare you the details, but basically the closer you stay to right at subsurface, the better for the control of the flow. So the idea with being able to open and close this and control this opening is that when you get to right about here, you can go a lot faster. So you can open this up and then pour much more quickly, push a lot more liquid through, and then raise the fill head as it goes. And that does a fantastic job of stepping the pressure down and mitigating it and minimizing the turbidity and the vorticity so that you can get a really nice pour really, really quickly. You can move a lot of liquid really fast without disturbing it too much. And then in that case, we can either use it based on a time function because there's enough pressure mitigation in here and enough adjustability that you can just say, okay, cool, we're dialed in. We know what the head pressure is. We've got that maintained and we know how long this takes. Or we can use it in conjunction with a flow meter to say, hey, we know exactly how much liquid went through here and we know it's ending up in the can. And that's awesome also. So in some instances, in order to mitigate this, there's the option of putting a buffer tank in. If you've got, again, pumps or anything else or huge tanks that you really almost need to step it down more. So sometimes in 300 barrel tanks, you can see it's coming out of here at like 20 PSI. So you can use a buffer tank to step it down and get a nice even 15, and then you get your nice even pressure drop out of here and solid control over your fills. So again, the advantage here is that you can get a lot out of a little. We can have a ton, you can have fewer fill heads and get the same CPM. You have a wide range of adjustability, so you can adjust both stages of the pour. You can say, okay, I want to go this fast for this first part, and then when we're going here, we can open this all the way up and just rip. So you can control both of those stages. Of course, the disadvantage with this is that it's complicated. You need to be well trained. You need to, your people need to know what they're doing. So there's a lot of subtlety to the adjustment here. It can be simple. Again, this is all if you're in the optimal product range of you're really cold, you're close to freezing, and you're at a medium carb level, it's simple. But when you're trying to push the boundaries, that's where you really need to start understanding some of this stuff and start knowing what you're playing with. So that is kind of how this one works. All right, next one. So let's go. This is top fill counter pressure. So this is also, this is a very tried and true method. You can see over here, we never modeled this, or at least I didn't have time to really, we never really modeled this. These are the patents on this system from 1954 is the original patent on a counter-pressure system, and it works basically the same now as most of the rest of them do. You can see there's a combination of, sometimes there's flow meters or sometimes there's sniff tubes to tell how full it is, but the general gist of this is the same. And in the traditional implementation of counter-pressure, you have your tank, you're coming out of there, whatever this is, you're just maintaining pressure here, and you're actually pumping it out into a pressure bowl. So what happens in the pressure bowl is this will fill up to a certain degree, and then you'll apply extra pressure. So a lot of these operate at 30, 40 psi, so then it's very highly pressurized in here, and so you're stepping way up, and then you're coming in here and pressurizing the vessel to slightly less than what is in the pressure bowl. And then kind of the difference between the pressure bowl and the pressure in the vessel is what controls your flow rate. So the filling part of it can actually happen pretty fast. And again, it depends on, there's obvious limits to this. As you get warmer, again, it's all in ideal conditions, everything's pretty fast. A lot of counter pressure marketing out there says, oh, well, we can fill anything anywhere. And it's like, well, sure, but why? Like, why do you want to fill something that's completely overcarbonated? Because you can get it from here to here, but eventually this has to be opened up again. This has to get a lid on it. So what that means is it's right back to my shaken beer here. If you rip this in and it's high carbonation and warm, it's going to take forever for this to come back down and be settled enough to really go to the off gas. So what you sacrifice here, and this is obviously a sliding scale, what you sacrifice here is time. So you can mitigate the pressure, and then you can, some of the methods are you will bleed this off, pause, bleed this off some more, pause, and then finally be able to release it. But what do you think is going to happen if you're coming in here at 35 PSI and then you quickly vent this to atmosphere? It's going to be the same thing as if I opened this beer right after I shook it. It's going to go everywhere, and that's what happens. So you have to, there's a mitigation here that has to happen where you can meter this off gas in a controlled rate and drop it slowly and gently so that you don't just have all that CO2 come right out of solution. The nice thing is there's pretty typically good adjustment on these things. So the advantage of this, of course, is the widest range of product conditions are available. Like if it's warm, you can do it, but it means you're sacrificing speed. It's well established. Again, this thing's been around since, this is a 1954 patent. Obviously, a few things have happened since then with microcontrollers, but again, it's basically the same idea. The disadvantages here are speed in terms of cans per minute per fill head. So I know everybody is sitting there going, well, how are you saying counter pressure fillers are slow? The lines at Coors do 1,200 cans a minute. Well, yeah, it's because they have multiple 48 head rotary rotary fillers working at the same time. If you have 48 fill valves filling simultaneously, it cuts the time down quite a bit. Whereas, if you have fewer fill head, so the time per fill head is actually slower, but you have more of them so you can go faster. Clearly there's a lot of complexity here. Sometimes this pressure bowl is, like in this illustration, it's a big pressure bowl that sits up here above this. Sometimes the pressure bowl is underneath. There's a lot of, this is a big stainless steel thing that has to hold pressure. Pressure in vessels is tricky. There's a lot there. And, again, it's complicated, but once you get it set up, it's there. And of course, with that complexity comes cost. So mitigate, that's the nice thing is as we go down down through these slides of what's here, typically it does come with, all of these come with a cost, and the more parts and the more stainless steel and the more sensors and the more everything else, you know, the more things cost and the more there is to maintain. So this is the top fill counter pressure. So I guess the other thing I didn't really make the distinction here of is typically there is a cone at the top of this. So as the liquid comes in, the cone at the top of this really pushes the liquid to the outside of the vessel and then comes down into here. So depending on how fast you do that, it can be gentle or not. So if this is a nice controlled, slow laminar flow down the side of the can wall, it'll be gentle. You won't get so much disturbance. If you're really ripping and going at really high flow rates, then you're dropping from here to here and you're pushing a lot of liquid, and you're going to get, again, I wish we'd modeled this, but we haven't. You're going to get a crazy amount of turbulence and everything else down here, which is ultimately going to break that out depending on where your pressures are. So I guess now we get to talk about really new fun stuff. And this is our new, just actually announcing it today with the patents pending, of how the Wild Goose counter pressure systems are going to work. So what we're going to do is, we still have our same system here. You have an optional pump or a buffer or pressurization tank. This is not necessary in this instance. So it'll be very much like our variable line restriction with, here's where we're going to get some of our pressure mitigation. And then we will also have pressure mitigation here. So we will also be able to seal the top of the can, pressurize it, vent out to control this pressure. But we also have excellent control over the flow rate via the line restriction, and we get a step down. So this pressure differential is not as big. We're not coming from 35 PSI to 0. Now we're coming from, we're coming from 15 PSI, stepping down through here down to 0. So you can see from where we've modeled this, what we get now is we have, and this is a slightly more fine-tuned model of the gas-liquid interface that's going on in the can, where we can see, basically, if we look at it down here, it's a little easier to see. The blue is still clear liquid. The red is still straight gas, but we can actually really look at where the mix is. So the gas-air mix is really what we're trying to control here. So by being able to vary the line restriction and vary the flow rates, we can have this subsurface and get this nice subsurface pour while maintaining our line control over this whole thing and maintaining the pressure in here. So what that gives us is the ability to actually basically have counter pressure when you need it and atmospheric when you don't. So if you're on the limits of, if you're trying to push your carbonation limits or your temperatures or what have you, and you need to be able to pour in outside of, the bandwidth there, and you need to have more control over this venting and step this velocity down to where it doesn't just vent to atmosphere so quickly, you can apply this pressure at the top and have control over this. And then if not, so the other part of this, to go back up here real quick, the other part of this whole thing is at the beginning of this, there are, for counter pressure systems in general, actually, you have to pressurize, typically you will, and again, typical is a big word here, but you have the option to like evacuate the vessel, especially like the Maheen bottling systems work this way. You have multiple options to evacuate, purge, and then pressurize and then fill. In this, you can do that, and you kind of have to make sure you're always pressurizing this can, especially if you're coming in here at 30 or 40 PSI. This has to be pressurized, which takes time, uses a ton of CO2, whereas now you have the option of controlling what that top pressure needs to be. So it doesn't have to be every can pressurized to 35 PSI, taking the time to do that and taking the gas to do that and the consumables to do that. Instead, you have control over how much you need. If you don't need any at all, you don't bother. You don't need it. In this case, in other instances where you do need counter pressure on the top of it, you can apply as needed and vent as needed. And the whole process is much quicker and uses much less CO2. So, again, that's sort of where we're at with how it works. Yeah. So, and of course, the advantages, I'm trying to be brief over here. The advantages and disadvantages of all these systems are, these lists are way longer on all these slides. Advantages here are we have the cool parts of the fill system that in our atmospheric system with combination of counter pressure. The disadvantages all come with it, right? You still have to adjust things. You still have to know what you're doing, and all of that. And we're hoping we're going to be launching. It's going to be available in January. So there's been a lot of testing. We've been working on it for almost 2 years now. And yeah, it's looking really promising, and we will have units available in the beginning of January. So now I guess, so who thinks this is ready yet? You think it's sat long enough to be opened? Let's find out. Because now we get the questions. There we go. Solubility takes time.
Thanks, Alexis. It doesn't look like we have any questions at this point. We'll give it a couple of minutes in case anyone has anything they'd like to ask. Do want to remind everyone that the slides for the presentation are available for download at the bottom of your screen there, and there'll be a recording shortly after we wrap up, the same URL, so you can rewatch the presentation in case you missed anything. Anything else you'd like to add, Alexis?
I'd like to thank Dennis for the encouragement. No, I think I hope I hope it wasn't. I brushed over a lot of science here. Obviously, there's a lot of complication going on. I'm just trying to tell, trying to make it as accessible and as much of a nice story that we can follow and and sort of know what we're dealing with. I'm happy to answer, more questions of how it all works, and or any of the more of the fluid mechanics or any of the rest of it, as needed. But I do see a couple of questions coming through the chat. Unfortunately, it is not going to be retrofittable. This has turned into a very different animal from what the Evo lines are. So it's going to be two different directions. The controls are all very different. There's a lot more going on. We have a lot going on in the control aspect of this also. It's a very, let's call it a very sophisticated machine. We're hoping that what that sophistication is going to do is make it incredibly easy to use like the rest of our machines, and still give the users the power to make all the adjustments that are necessary and have total control over their system as they go.
We do have a couple questions that have come in here. First one here, most popular. Can you give a brief description of how your flow meters work?
So we actually have, there have been a number of different ways. The current flow meters that we have are a vortex flow meter. So they have, if I understand it correctly, there's it's basically almost like a little airplane wing or a fin that's in the middle of it and a piezo on the inside, so that as it vibrates, as liquid goes by, it'll, liquid's flowing this way, and the tail end of it flutters very, very subtly, and we get flow counts that way. We have had basically every configuration of flow meter has been through our lab. We are now very actively working with and integrating. We want to make sure we're getting as accurate a reading out of them as possible. With the magnetic flow meters, those are looking very, very promising. But again, we want to make sure most flow meters, unfortunately, are designed to be run constantly. So you get, if you're always have liquid going past it, they do a great job of totalizing what's going on. When the liquid is stopping and starting, it gets more complicated. It gets lumpy. So we're working on ways to make sure that we're getting good readings out of the ones that we have, but there are some new ones that are effectively magnetic, that have a clear tube all the way through, so we don't have any interference. We don't have to worry about particulate clogging them, and get really nice, accurate results out of them. So we're clearly we do our homework. We want to make sure that anything going out to someone's facility is thoroughly tested. We know how it works so that we can explain how it works to you and make sure that it is doing what it's supposed to. So yeah, that's the long answer for how the flow meters work.
Excellent. A bunch of questions came through here, so we'll just keep moving. Next is counter pressure filling most important for higher temperatures and carbonation levels? Sorry.
Yeah, so if you're trying to can at 38 degrees with a 2.9 carb, you need a counter pressure system. I like to think about counter pressure kind of like four-wheel drive in your car. We're in Colorado. Every vehicle I've ever owned has four-wheel drive in it. But realistically, how often do you really use it? The answer is I probably use it once or twice a year. So, if you need it, you need it. And if you find yourself in these product conditions that are the equivalent of, trying to go rock crawling in Moab, and you need, huge tires and four-wheel drive and locking differentials and everything else, and all of these things to say, I'm trying to go to these extreme conditions, my answer to you is maybe find the pavement, go around the other way, because you can do it. It's not going to be fast, and you don't want to be doing it every day for your commute. So work on, finding these things. One of the things that we really find with carbonation levels is people will shoot for, I need to have super high carbs, so I'm going to shoot for 3.2 and hopefully I'll get 3 or 2.9 in the can. Whereas really, if you're managing all your pressure and you're managing all your carbonation really well, the better answer is to shoot for, 2.9 to get 2.8. So if you're over carbing, it just makes it that much harder to pour. Whereas getting closer to your target value at the end of it and making sure it's cold and everything's really well settled gives you don't have all that carbonation loss. And I guess it even goes, people, I think there's this misconception that even, everybody seems to be making seltzers now. And there's this misconception that seltzers are carved at 3 or 3.2 or whatever. Go grab a Truly or go grab a White Claw or anything else and put it through your carb box. They're carved at 2.5, just like everything else. So yeah, anyway, sorry for the long-winded there. What's the next question?
Next question up: on a typical inline atmospheric filler with variable line restriction, what ID of transfer hose is recommended from the product tank to the packaging line to avoid foaming due to the change in line size?
We typically just do an 1.5 inch brewer's hose. It depends on how fast you're going. If you're doing any of our 1 to 5 head, an 1.5 inch line works great. What we have seen when you're going on some of the 6 or the 8 and 10 head machines is that it actually pulls too much liquid if they're all pouring at the same time. So sometimes you need to run a 2 inch or 2.5 inch lines into the manifolds. We've seen that work a couple of different ways. So that's the other part of it, right? Is you do need to make sure you can feed enough liquid into this stuff, because that's another place where you're going to get a pressure drop. If you're emptying the bucket faster than you're filling it in those lines, you get pressure drops in small lines if you're not pushing enough liquid through them.
Excellent. Next up from Eddie, says we're looking at a small canning line, 30 to 60 cans per minute with a 2000 L run. Do you need a counter pressure system, or is the atmospheric acceptable? Complete newbie here.
So it'll come right back to how cold can you get your bright tank, and what carbonation do you want your carbonation to be? If you're shooting for a 2.5, 2.6 carbonation and you have a good glycol system and you can be pushing at reasonable temperature, then it should be fine. So now wait, I may have misheard that though. If you have a 2,000 meter run or a 2,000 liter run?
2,000 liter, it looks like.
Okay. Then you should be fine with, either system will work. And again, the biggest part of what we're trying to talk about here is there's nothing simple about this. Anybody that's even tried to pour out of a keg in college knows that if you're not doing it right, you get nothing but foam. So any system that you get, you have to be prepared to work with it and learn it. And, having a dedicated trained operator is absolutely the key to success in any of these things. None of these aren't appliances. There's nothing out here that even if you go spend $3 million on a KHS system, they don't just drop it on your floor, turn it on, and walk away. It takes months to dial one of those things in. So you just have to be committed and know that there's adjustments to be made and knowledge to be gained, and you need to be paying attention and learning how these things work.
Excellent. Next up from Rodrigo, is IR retrofittable for all gooses?
The counter pressure, unfortunately, it will not be retrofittable. I think I said that a little earlier, but the control, it's a very different animal. All the controls are different. The configuration, the seal bar is very different. The way that it goes. So the methodology and the technology is all kind of the same, but unfortunately, we tried at the beginning to do a lot of different ways to really make it so that you could add counter pressure heads to the existing Evos, because that's the way we like to do things. But in this instance, it just flat out, it didn't prove reliable enough in testing, and it didn't prove to give the level of refinement that we demand. So it just, we had to go a different direction.
Excellent. Next up from Brad, do you always recommend using buffer tanks if possible before the filler?
Again, it depends on whether or not you need them. If you have huge tanks and long runs, it makes a big difference. It really will help out a lot. If you've got a 60 barrel bright tank and you're 15 feet away with your canning line, you don't need one.
Okay. How much does beer density impact CO2 solubility in the filling process?
Actually, quite a bit. So there's a lot of things that'll go in there. So your density, and again, there's not like I don't have a rule of thumb. My experience in the specifics of that aren't as deep as they need to be, I guess. But no, density, the amount of dissolved organics in it, the viscosity, the amount of surfactant, is it, you notice Pilsners foam differently than IPAs, foam differently than stouts. It all has to do with the density and the organic compound, the organic content of that specific recipe. So yeah, it makes a huge difference. I know I actually just very recently learned that there's a completely different carb temperature, temperature pressure chart for water than there is for beer. And for, so if you're doing seltzers, it's almost better to be using the water carbonation versus the beer carbonation, because there's so much less in them.
All right. Next up, how many different models will the counter pressure filling be available on?
So right now what we have is we're looking at a 2, a 4, and a 6 head configurations. I think I'm going to get stuff thrown at me from people in the building if I talk too much about what's available when. But we're testing all of them, and I know we are planning on delivering systems in January. So if I say that, you can get a 6 head with all the bells and whistles on January 1st, someone's going to come in here and scalp me on camera. So we're not doing that.
All right. Let's see. Next up, this one comes from Darren. We purchased a Wild Goose canning line recently. It's been great. Question, what is the upper temperature range for reliable can fills? Colder is better, but what about when the temp starts to raise at the end of a can run?
So, okay, as temperatures are raised, this happens a lot. As you get into the bottom, the cone of your tank, things start to warm up. The trick is to push through it and go as fast, and don't stop. But the other part of this here is, and then obviously there's limits to adjustment on what you can really do. But when you start getting warmer, you have to start slowing down. So you can, again, if you're happily cruising along at 33 degrees, and then you get into the bottom of the tank and it starts to warm up, the trick is to keep everything cold, don't stop, and then up your line restriction and slow everything down in order to, again, sort of reduce a lot of the factors that we were just talking about and make it as gentle as possible. So those last, the last barrel or whatever that's in the can that's sort of steadily warming up, temperature is your enemy. You got to get through that as quickly and carefully as you can. And just to completely contradict myself, if you pour a little slower as you're getting through those, it'll help. So you're not, again, it's the beer through the fire hose thing, right? Like if you're pouring way too fast and it's really warm, you're going to get nothing but cans of foam.
All right. Next up is the fill rate for your subsurface counter pressure systems comparable to traditional counter pressure fillers?
In theory, it's going to be significantly faster. We have the subsurface variable line restriction that we have. We can get a full 12-ounce pour in like right around 2 seconds, 2.5 seconds, something like that. That's really, really fast. So the more that you add on the pressure on the top of things, the more it slows things down, which isn't necessarily a bad thing. I mean, if you want to go faster, you add more fill heads in some ways and what have you. But again, we're trying to get the most out of as little as possible. So the ideal situation is you're carved at 2.5 and you're at 32 degrees and you just rip. It's dialed in and everything pours really fast. I think that's sort of the gold standard for speed per fill head. And as you know, so that option will still be a thing with the counter pressure systems. And then as you need as you need the pressure assist and everything else on the top of the vessel, it's inherently going to slow things down.
Excellent. We have a ton more questions here. We'll get to a couple more of them, but the rest of them I'll send to Alexis. We can post the responses back with the recording after the fact, but we'll do a couple more here. Next up comes from Scott. He wants to know, how does the counter filler compare in price and cans per minute to the Evo series?
It should be pretty comparable. It's going to be a little more expensive. We have not pinned down 100% of the bill of materials on things yet. So it'll be comparable. Likely it'll be a little more expensive, and part of it will be, again, throughputs. We don't have enough of them in the wild to give a really firm number on it. We can always do lab testing, but we're not going to give you a throughput number based on what we pour with water in ideal conditions. We want to get more of them out into test facilities and really see what's practical before we start quoting throughput numbers.
Okay. Will the new system coming out in January be available for bottle filling, or is this purely canning only system?
This will be a canning only system. If we have a lovely counter pressure bottling system. If you want bottling, we can do that all day long, and we can get you one way before January.
All right. Wondering about headspace and contamination when canning carbonated water.
Okay. That's all. Okay. So yeah, water, the nice thing about alcohol is that it kills all the bugs. You need to be careful with a lot of things with carbonated water. Headspace, I don't know if that headspace would be the one that I would be concerned about. I think what I would really be concerned about for contamination in carbonated water would be making sure the cans are well cleaned before they go in, making sure everything is basically aseptic and cleaned. And then, to be perfectly honest, I don't know that much about if they pasteurize, LaCroix or not. It turns into the fun area of we're getting into a food product versus an alcoholic beverage, which means now you're not dealing with the TTB, who say what you will about them, seem much more agreeable than the folks down at the FDA. So I don't, I can't really speculate on contamination in non-alcoholic stuff because I don't really know much about it. I just know it's, you have to have your cleaning procedures in place. You have to have, and you have to be, following FDA guidelines.
All right. Next up from Matthew, is there a roster of expertise that Wild Goose relies on that we can access?
Absolutely. I like to say we have the best and brightest service techs in the business. We have a phenomenal group that is shockingly available at most hours of most times, and we are now setting up service in a number of different locations around the globe. We have well-established service and sales in Europe. We're getting it going in Asia. We're getting it going in. We have a well-established service in Australia. So we're trying to make sure we hit most of the major regions to be able to have local in-language service there. But our service techs are incredibly well trained. I don't think there's a single person on the team that doesn't have at least 6 years of packaging experience. Most of them have at least 6 years of packaging experience on Wild Goose equipment, so they really know what they're doing. And we have, I don't know, it's probably pretty close to 1,100 systems installed now. of just the canning stuff. So we know the problems, and we know the solutions. If you're having problems, they might shoot at me here, but if you're having problems, call them before you get pissed off. If you're having a frustrating day, and it happens to everybody, call before you're angry. They would much rather talk to you and walk you through an easy problem than being in the state of wanting to throw wrenches across the room and calling and saying this machine doesn't work because of XYZ, when they've likely seen this problem before and can talk you through it.
Excellent. We'll do one more here, and then we'll post the responses to the rest after the fact. But our last question for today: would you prioritize making low flow adjustments on the restriction plate in the beginning of the run when trying to get weights, or is it something to adjust once we have our weights and we want to control how much product we are losing?
So there's actually, with the way the goose stuff works, typically when you're trying to get that perfect, really nice looking clear pour with just a little bit of foam on it, a lot of that magic happens at the low fill. So if you get that low fill dialed in right at the beginning and really get the nozzle buried, and then you can adjust your high fill as needed. Obviously, if you're trying to adjust the high fill for very subtle volume adjustments, you're dealing with a lot, it's a higher rate, so your error margin is probably a little higher. We do have the option of going back to low fill at the top of the fill, which if you're really flying and you're really pouring a lot of liquid, you want to have that nice step back down in pressure before the nozzle comes out and before you close the nozzle at the top, so you can sort of ease the pressure back in by turning the low fill back on at the end of the fill cycle. And in that case, that's where you would make that adjustment.
Excellent. Well, that's where we're going to wrap up for today. Again, reminder, the slides for the presentation are available for download at the download presentation button at the bottom of the screen. The presentation will be available to rewatch shortly after we close this out today. And I'll get all these remaining questions over to Alexis. We can get some written responses to those and post back with the event. So if we didn't get to your question, don't worry. We'll get it posted with this event shortly after we wrap up. Thanks to Alexis. Thanks to Wild Goose for today's presentation. Lots of great information there. Alexis, do you have anything else to add before we wrap it?
No, just please don't hesitate to reach out with questions. And I hope we can, if we don't know the answer, I'm sure we'll be able to make something up for you. So
thanks, Alexis. Everyone have a great day.
Thanks.